Even on Zoom, no one's here.
Did anyone else go to your office hours about the same issue or?
No, you're the only one. I think most people are working on the meshing right now.
Okay.
But I did email the dev team, so he did give me something to try. So I'm gonna try it when I get back from now.
Oh, okay.
Yeah.
Sounds good.
Right, it seems like a consistent thing on Windows, so I think that's probably the issue.
Did you try yours? Did you try yours?
So when we did the workshop, I used my own laptop. So my laptop has an older version of Vascular. But I just reinstalled a new one on my office computer, so that's why I think the issue might be with the newest version. So yeah, I'll go back and double check it and see. All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? Good, hanging in there. We got just 2 more weeks to go, and then we're done. So almost there. Okay, so like I mentioned last week, the plan for the rest of the semester is just to kind of give you guys time to work on the project for the most part. So for today and Thursday, I do have some lecture slides just to kind of give you some, just to kind of fill in the gaps in terms of the cardiovascular system. We've been focusing mostly on the arterial side for arteries, but you know, there's a lot of interesting biomechanics that happens in the veins and the microcirculation. So last Thursday we talked about veins. Today we're going to talk about microcirculation, and then this Thursday, probably the last time that I speak, kind of in front of the class, we're going to talk about what's called low phantom, which is an important thing for experimental cardiovascular healing. So I don't think that these lectures are going to take the whole time. In fact, I think the lecture today probably will be done in about 30 minutes. And so for the rest of the time, in today's lecture, the rest of the time in Thursday's lecture, I wanted to kind of leave it open to for you guys to work on your projects, for you guys to come and ask for help, things like that. So, I want to make sure that there's enough office hours, just because, setting up the mesh, setting up the simulation, can be a little bit complicated. So, I know we did a workshop, but we kind of did it a little bit quickly. So, and if I feel the need to go over some things again together, I'll probably do that beginning of next week. So next week I don't really have anything planned. So next week is just gonna be all open office hours. And so definitely you want to, at least, take the class time, work on your projects. If you're running into issues, that's definitely the best time to come for help. Some people have already kind of, gotten started with the mesh. I think the majority have been answering kind of mesh questions, but if you're starting to run simulation, that's good for that as well. Okay. So one announcement with regards to that. It looks like there is an issue with the Windows version of Cardiovascular in terms of producing the simulation files. So I'm working through that right now. I'm in contact with the dev team, and hopefully we get a fix soon. And so I think at least for this week, at least for the next couple of days, I really want to encourage you guys to work on your mesh. So making sure you get a good mesh. Remember, for the most part, you guys are aiming for meshes around maybe 500,000 to 1 million elements. I think that's a good amount of elements for you guys to aim for. But if you're going to run a test simulation on your own computer, I would aim for the ballpark of maybe 100, 200,000 elements. Anything beyond that, it gets a little bit too slow to work on your own home computer. Okay. All right. So the other thing that happened, I just finished late last night, right before going to bed, was I finished grading your guys' exams. So I have them here for you to pick up if you want to take it with you. I didn't even get a chance to look at the averages. I finished and I just went to sleep right afterwards. So, I think the averages are on Canvas. So you can check it out there. But yeah, you can come pick up your exams here. Okay. All right. Any questions I can answer before we get started for today?
You might have just mentioned it. So, but next week, are you gonna just have the class open?
Yeah.
Or open?
Yeah. So I'll be here during the lectures. So bring your laptop so you can work on the projects. You can just kind of flag me and just ask questions for me. Cool. So it'll be like that today as well. So I think this maybe only like 20, 30 minutes for this. There's not much to cover. Okay. All right. So let's go and get started. Okay. So like I mentioned, today's topic is the microcirculation. So, for this class, we spent basically the entire class talking about arteries. Honestly, arteries are kind of the most interesting thing. That's where most of the disease happens, and that's where flows and pressures are highest. Last Thursday, we talked about veins. Veins kind of have their own issues, but usually not nearly as much as arteries. And so in between the arteries and the veins in your cardiovascular system is the microcirculation. So this includes all the capillaries, all the tiny arterioles, venules, any vessel that's kind of too small to pick up with a CT scan. That's kind of what we're talking about today. Okay. So let's remind ourselves, what exactly is the microcirculation? So the microcirculation refers to kind of the network of arterioles, capillaries, and venules that are located in all the human organs that allow transfer of oxygen and molecules to the blood and to the organs, right? So we've mentioned it kind of many times throughout the class that the main purpose of the cardiovascular system is to transport oxygen and nutrients to the rest of the body. All of those oxygen and nutrients are kind of embedded within the cells, blood cells that kind of flow along the cardiovascular system. It's not until those blood cells come into the microcirculation that those nutrients and oxygen can kind of be offloaded into the muscles and organs of your bodies. Okay, and so that's what we refer to as the microcirculation. And so the size of the vessels here in the microcirculation ranges from anywhere between 10 to 100 microns for the arterioles. For the venules, these are the kind of the smaller veins here. They range from anywhere between 10 and 200 microns. And the smallest microcirculation, which is the capillaries, these are anywhere between 4 and 10 microns. So extremely, extremely small. For the most part, you're not going to pick these up on any kind of CT scan or MRI. So everything that we know about the microcirculation is done You know, usually through ex vivo kind of environments where we take kind of cadavers and kind of and people outside and examine things under a microscope, just because it's really hard to observe this phenomenon in a living person, just because it's, you know, you can't really put a person's muscle underneath a microscope. Okay. Because of their small size, there is a considerable amount of pressure, pressure drop and pressure loss through the capillaries. Remember, you know, our kind of our classic formula for the flow resistance in a vessel, right? It's something, but you know, the most important thing was that it has a dependence on the vessel radius to the fourth, right? And so the smaller the radius, you know, the higher the resistance. And so, and then this scales up to the fourth power. And so you can imagine for the smallest vessels, you have a tremendous amount of resistance in these capillaries. And so you have a tremendous amount of pressure loss and viscous loss, okay? And so, and the capillaries are kind of the main reason why your arteries generally are higher pressure, higher flow. But then when you get to the veins are much lower pressure, much lower flow, mostly just because the blood loses a lot of its energy going through the capillaries. The other interesting thing about the capillaries and the microcirculation is that lining all the vessel walls in this section is, you know, a bunch of smooth muscle. Okay. And so actually the arterioles and capillaries and the venules, they have a very, very interesting ability to kind of expand and contract themselves actively. And so not only just, you know, expand and contract, you know, passively in response to the flow, but they can actually actively control their diameters, you know, better than any other part of the circulation itself. And that really does a really good job of regulating the flow there. So we'll talk quite a bit about that today. Okay. But the main thing that you need to know about the microcirculation, this is where all of the nutrient and oxygen exchange happens, right? So typically, you know, blood cell comes in through the arterioles, it's full of oxygen, it's full of nutrients, it flows into the capillaries, into the microcirculation. What happens there is that it's almost like an Amazon delivery system where, you know, you drop off, you know, the oxygen and drop off the nutrients into the organs, right? And then any kind of waste product, any kind of carbon dioxide that the muscles or the organs no longer needs, and then puts those into the blood cells. And then as the blood cells move outwards, then it goes back to your lungs where it kind of offloads those things, or the blood flows to your liver or your pancreas, you know, things like that, you know, to transport. So you can almost think of the capillaries as kind of like the homes, I guess you can say, right? Where if we kind of use the analogy of kind of an Amazon delivery system, the arteries and the veins, those are like the freeways, those are kind of like the highways of your cardiovascular system. And then, you know, the Amazon delivery truck's driving on the freeway, and then once it arrives at the home, then it drops off all the packages inside the microcirculation, and then kind of makes its way back to the distribution center, and then, you know, kind of is on this kind of endless loop just like that. Okay. All right, any questions on this so far? Okay. All right, so let's talk a bit more about kind of the four functions of the microcirculation itself. So the first, I would say, purpose of the microcirculation is to provide resistance to flow, right? Remember, these are the smallest blood vessels in your body. Most of these blood vessels are just thick enough so that one blood cell can kind of squeeze through there, right? And so that's very different from all the other blood vessels in your body. Or, you know, your aorta is so thick that it has, you know, millions of blood vessels inside it at any given time. Okay. And because, you know, these microcirculations are lined with smooth muscle, they can kind of expand and contract themselves, kind of regulate the flow. And so whenever you're in a situation where you need to increase blood flow to a certain area or decrease blood flow, whether you're exercising, whether you have an injury, you know, your microcirculation plays a really big role in terms of, you know, driving the blood into certain areas of your body, either by constricting certain areas or expanding. You know, regulation of flow or resistance of flow is a really big role for these capillaries. Okay. The function number two, molecular exchange. So we just finished talking about this, and so you know, the capillaries are so small that it allows kind of, you know, exchange to occur between the organs and the muscles and the blood cells. Okay. It's one of the only places where the blood cells are able to make kind of full contact with the vessel walls all around it because they're that small. Okay. Another function is flow bypass. And so unlike other parts of your body, your microcirculation actually has a really great ability to create new blood vessels. And so, you see this more than anywhere. So this is called angiogenesis. We'll talk about that in a bit. But, let's say that you're in a situation where you need more blood flow to a certain area, whether you're exercising and a muscle needs more oxygen and needs more nutrients to function. The microcirculation actually has a great ability to form new blood vessels like this, right? So that certain areas of your body can be perfused with blood, perfused with oxygen more so than anything else. Okay. All right, and so the last function for the microcirculation is capacitance for compliance. So it's not a major function. Generally your larger arteries are better at blood storage, but the microcirculation, there's just so many of these tiny vessels in your body that they do actually contribute to some blood storage as well. So at any given time, about 22% of your total blood volume is stored within the microcirculation. Okay? So it's not that much, probably the majority of the blood is stored into your veins, but it's still a pretty decent. Okay. Okay. All right, so this plot right here just kind of shows you the amount of pressure loss that occurs as you flow through the arteries and the microcirculation. Okay? So the way to kind of read this image here is that on the left side of here is the arterial side, on the right side of here is the venous side, and then right in the middle here, this is where all of the microcirculation is, right? So blood flow generally flows this direction inside a human body. Okay? So you can see in the arterial side, your blood pressures are very high. But then when you start flowing through the microcirculation, you have a very sharp decrease in the pressure, right? And then once you kind of flow through the microcirculation, the pressure there still is some relative pressure drop in the venous circulation. Otherwise, there would be no blood flow in that region. But you can see the pressure drop kind of slows down quite significantly. Most of the pressure drop occurs kind of right before you get to the microcirculation. Okay? And you can see that the blood velocity, because the vessels are so small, the blood velocity also reaches a minimum within the microcirculation as well. Okay. All right, so this figure actually is very interesting because it is actually taken. A lot of data has been taken for this figure as well. And these lines that you see here are just kind of the regression lines that are the average. Okay, and so because they're so small, and because the blood cells kind of take up such a big chunk of the flow inside these vessels, the biomechanics and the fluid mechanics of the flow here is actually very interesting. Okay, so the typical size of a blood cell is about 7.5 microns in diameter and about 2 microns in kind of thickness, right? So this is way smaller than most vessels in the body, but this is about the size of a capillary, right? And so if you look back to a couple of slides, the capillaries are around 4 to 10 microns, and so this is just about the size here. And so when the blood reaches the microcirculation, and the vessels are kind of just the perfect size for these blood cells, these blood cells kind of have to squeeze through the microcirculation so that there's a ton of contact, right? And it's because there's a lot of contact, that's how the molecular transport or the nutrient transport, the oxygen transport, that's kind of how it takes place. Okay. But because of the small diameter and because of the kind of the viscosity of the blood flow, this also creates some interesting effects as well. Okay. All right. So one of the really interesting effects that you'll see is something called cell migration and cell depletion. And so because these particles are so big relative to the size of the vessel, what tends to happen in these situations is that, by itself, all of the particles or all the blood cells will naturally start to kind of congregate near the walls of the vessel. Okay. So what you're seeing right here, this is a vessel in the microcirculation, but maybe we're not quite at the capillaries yet. And so this might be like an arteriole, which is kind of a very small artery. Where maybe the diameter of this vessel is maybe on the order of, I don't know, maybe 30 micron or something like that. Okay. So not quite small enough for just one cell, but the cells are starting to get crowded here, right? And so when you're in this kind of situation, and this is true, for any kind of flow, actually, not just blood flow. So if you take maybe you take some fine grit sand and you try to flow it through some small microchannels, what you'll see is that the particles or the the things that are suspended in the fluid will just naturally kind of congregate towards the walls. And this is a very kind of well-studied effect called the Seeger-Silberberg effect. Silberberg. Okay. Seeger-Silberberg. I always mispronounce that name. And it's been observed for a wide variety of particles. So it's a very kind of interesting thing. And it's kind of part of it is kind of due to kind of the molecular forces kind of between these particles here, and its interaction with the fluid. Okay. All right. The other thing that you'll notice in this kind of small particle flow is variable viscosity. And so, one thing that you hear about is that blood is a non-Newtonian fluid, partly because the viscosity of blood tends to vary, but you only really see those effects in kind of the very smallest arteries like this. So yes, blood is non-Newtonian. Its viscosity does decrease when you increase the shear. It's what's known as a shear thinning fluid, but you only observe that in kind of the smallest vessels. Okay. It is quite significant though, and so if you measure the viscosity in some of the smaller vessels, it can be up to a 5x difference, which is quite huge. All right, any questions on this so far? Okay. And so because of those two previous effects, you can kind of see some really interesting behavior in the microcirculation, right? And so in some of the larger vessels in the microcirculation, you see kind of an accumulation of the blood cells, right? Like this. But they tend to kind of avoid the wall. So this effect is called plasma skimming. Okay. But then once you kind of reach kind of the smaller vessels here, it's only really big enough for just one cell at a time. And so the cells actually come in kind of single file. Okay. And so, if you kind of look under a microscope for blood, you'll kind of see this effect right here. Okay. And so because of this, the hematocrit, which is, if you remember, that's kind of the red blood cell concentration inside your blood, that tends to be reduced in the microcirculation, having values about 0.25, whereas, for most of your arteries, you have a higher concentration of red blood cells, which is 0.4 to 0.5. Okay. Part of this reason also is the fact that there's just a ton of microcirculation vessels. I haven't really shown a figure here to kind of illustrate that fact. But for any kind of big vessel like this, right? So let's say this is your aorta. The microcirculation is something that looks kind of something like this. And so there's just so many of these vessels here, right? There's just so much more places for the blood to go. And even though these vessels are so much tinier than the bigger vessels, there's just so many of these tiny vessels that that a lot of the red blood cells tends to kind of spread out through these vessels right here. Yeah, kind of did kind of a small facsimile of that there. So because of that, because there's so many microcirculation vessels, the hematocrit tends to drop, right? So on a per volume basis, you see less red blood cells, partially because there's so many, but also kind of partially because of the interesting kind of fluid mechanics that occurs at the micro scale as well. Okay. So another really important effect that you see in the microcirculation is something called the myogenic effect, or some people call it the Baylis effect, which is named after the scientist that discovered this. Okay. So remember, like I mentioned, that your microcirculation is lined with all the smooth muscle, and that smooth muscle can actually actively change the diameter of your microcirculation in response to certain changes in the rest of your body. Okay. In particular, your microcirculation is always monitoring your arterial blood flow. So that's the blood flow in kind of your major arteries. And depending on that pressure, it can modify its radius to accommodate that. Okay. So for instance, when the blood pressure in your arteries increases, the smooth muscle in the vessels actually contracts. So your microcirculation ends up with a reduced diameter compared to normal. And the opposite is true as well. So when your blood pressure decreases, the smooth muscle in your microcirculation tends to relax, which lets the arteries expand. Okay. So this effect, it was noticed it was first observed in 1903, and it's called the Baylis effect, and obviously it was named after the guy that discovered it. Okay. The main purpose of this effect is to maintain blood pressure within the capillaries. Okay. And so because the vessels are so small, just to make sure that that there's no damage to the capillaries, there's no damage to the cells there, your body needs to very carefully regulate the pressure and flow within the capillaries in the microcirculation. And so part of regulating that flow is this kind of myogenic effect, or the Baylis effect, where it kind of proactively changes the diameter to make sure that, you know, flow is relatively constant in those vessels. Okay. Another aspect that can occur in the microcirculation is something that we talked about last Thursday for the veins. And so because the microcirculation is so embedded within your muscles and so embedded within your organs, they actually receive a lot of external pressure from a lot of the tissue that's surrounding it, right? And so it's kind of almost like, you know, all these microcirculations are kind of encased in kind of like a muscular kind of sleeve. And so that those muscles, they're kind of naturally impart some pressure, okay? And so if you remember from last Thursday, this pressure is called the transmural pressure. Okay? And so this pressure results not really from the fact that the external tissue is actively squeezing, you know, but it's kind of more due to the fact that the internal blood pressure is so low that, you know, some of this is lost due to kind of viscous resistance and kind of this difference in pressure. Okay. So the relationship between the diameter of the microcirculation and the transmural pressure is generally nonlinear. Okay. And of course, this effect is kind of you know, regulated by the smooth muscle as well. Okay. And this is all kind of part of the myogenic effect too. Okay. All right, so these are a couple graphs here. So this graph kind of shows you the stress strain curve. So you can see that due to the myogenic effect and due to the transmural pressure, you have a very nonlinear kind of stress strain curve. Okay. Biological materials in general just have very nonlinear stress strain curves because of their, you know, because of their active components and because of their kind of their you know, nonlinear type of materials. Okay. And this plot right here shows you kind of the relationship between vessel diameter and the blood pressure, and you kind of see kind of as the blood pressure increases, you kind of see this this myogenic effect basically occur here, right? Where, you know, for the you know, for the microcirculation, where you can actively kind of change the blood vessel diameter, you know, you can see that the microcirculation is kind of modifying it there. Okay. All right, so let's talk a bit about flow pulsatility. So kind of right before the midterm, you know, we talked about the Wormersley effect, or the Wormersley velocity profile. And that's and remember that kind of have to do with the effect of, you know, because the blood pressure and because the flow rates are pulsing, they're kind of constantly changing in your cardiovascular system. That affects kind of the velocity waveform that you see. Okay, and so for a very long time, you know, because the microcirculation is so small, and because of the you know, because the flow in there has been assumed to be relatively constant, you know, it was assumed that there's not really that many pulsatile effects within the microcirculation, especially because, you know, the impedance inside the microcirculation is so large. You know, most of the pressure waves end up just reflecting off the microcirculation coming back. But it's been kind of a relatively new development that, you know, after some kind of observation, there is still some pulsatility within the microcirculation. It's just very muted compared to the arterial system. So some of this is just due to just arterial pressure oscillation. So, you know, so the pressure oscillation that comes from the heart, naturally that kind of trickles down to the microcirculation. There's some pulsatility due to the myogenic effect. So that's the Bayliss effect that we just finished talking about. And tissue compression as well. And so kind of this transmural pressure, this pressure that these blood vessels experience from kind of the external organs and the muscles, that causes some pulsatility as well. Okay. Let's talk a little bit about wall shear stress and adaptability. So, you know, we've talked a lot in this class about, you know, the fact that you know, blood vessels really enjoy homeostasis, which is basically a state of kind of experiencing the same amount of stress as it always has, and the capillaries and the microcirculation is kind of no you know, no exception to this. Okay. So wall shear stress, you know, tends to be higher on the arterial side, but then as you go through the microcirculation and the diameters drop dramatically, you know, the wall shear stress tends to kind of drops dramatically as well. Okay. And this kind of you know, changes dynamically as well depending on the state of the person. So, you know, let's say for instance that you like to exercise a lot, right? So when you exercise, your heart rate increases. That dramatically increases the blood flow in your body, and so that increase actually increases the amount of wall shear stress that you experience as well. And that wall shear stress is carried into the microcirculation as well. So one way that your body deals with this, one way that kind of helps to regulate the wall shear stress, is just by simply creating new vessels. Okay. And so through a process called angiogenesis, right, your body has the ability to form newer microcirculation vessels, right? So let's say that, you're inside your muscle here, right? And you have some microcirculation that kind of goes like this. What can happen is that if the wall shear stress inside these vessels gets too large, a new blood vessel may form like this. Okay. And that's actually very beneficial for your body as well, because as you exercise more, as you kind of demand more oxygen and more nutrients for your muscles, maybe the current amount of microcirculation is not enough to deliver everything that it needs. And so new blood vessels can form so that, new pathways can occur to deliver oxygen and nutrients as they are needed by the body. Okay. And so, if you actually looked at a scan of, a person that exercises regularly versus a person that, that kind of sits on the couch all day, like myself, you'll see that the person who exercises more regularly has a much more well-defined microcirculation, just because their muscles and their body just have much higher demands for oxygen and nutrients. Okay. And generally speaking, you really want to have a very well-developed microcirculation. Just because, having more, having more access to oxygen and nutrients from your organs is always a good thing. That means your organs and your muscles are performing well, they're performing optimally, right? And so this is kind of another good reason to kind of, making sure that you're exercising regularly, just for your cardiovascular health. Okay. All right. Any questions on this so far? Yeah.
Is the opposite of this true? Like, if you become less active, do areas, I don't know, retract?
Oh, yeah.
processes?
Yeah. No, that's true. Yeah. And so you see that a lot actually too. And so, the more kind of sedentary that you are, the less that you use muscles. I mean, part of it is your muscles atrophy, but through atrophy and through misuse, then, a lot of these microcirculations kind of close up on their own. And so your body basically is like, oh, you don't need this. And so we're just not going to maintain it. Just because, it does take some work for your body to kind of maintain a vessel like this. And so if it's not needed, then, your body just kind of closes. Yeah, that's part of the reason why if you haven't exercised for a while, even if in the past, maybe you were capable of running, 5-6 miles. If you haven't done that in a couple of years, and you try to suddenly run 5-6 miles, it's extremely difficult. And part of the reason is because, your microcirculation isn't quite developed anymore. And so part of it kind of dies off. And so even though, your mind remembers you kind of being able to run 5 or 6 miles, your muscles just aren't able to get the oxygen and nutrients that it needs at the rate to kind of sustain yourself for exercising that long. So, it's really good. Really, that's why, it's really important to kind of maintain a good, healthy, active lifestyle to kind of make sure that your microcirculation is still well developed. Oops. Okay. And so here's kind of a couple more graphs here to kind of show you kind of the wall shear stress as a function of diameter, okay, and the pressure as a function of wall shear stress as well. Okay. So I think these were taken from three separate patients, as indicated by here. So I think I have the exact, yeah. So if you want to learn more about the study, you can check out kind of this this source here. Okay. So let's talk a bit about molecular transport, because this is kind of the main, role of the microcirculation. So, we've talked primarily about the fluid mechanics, but, being able to transport nutrients and molecules is something that's really important. Okay. So how does this happen? So how is it that a molecule is able to, leave not only the bloodstream itself, but the cell within the bloodstream? So the primary means of transport is diffusion. Okay. So diffusion is the passive transport of a material through a region, and the reason it's passive is because things naturally tend to flow from areas of higher concentration to lower concentration. Okay, so generally speaking, when a blood cell kind of flows through an area like this, it's very saturated with oxygen, so it's may be carrying kind of a oxygen molecule or several oxygen molecules, and so it's very saturated. But compared to the tissue that's around it, right? Almost certainly the tissue that's around it is going to be oxygen deprived, or maybe that's not the right word for it, but it has much less oxygen than the blood cell itself, right? And so the natural thing that occurs in this situation, and which is facilitated by the contact that's done through the capillaries, is that the oxygen kind of sees that, hey, it's kind of crowded here. There's a little bit too much of me. So let me go to the area where it's less crowded, which is inside the muscles and inside your organs. Okay. And so that's generally how things are transported, through just simple diffusion. Okay. The thing that facilitates this for the microcirculation is that the vessels are so small that the blood cells can actually make physical contact with the vessel walls here, and that kind of facilitates and allows the transport to occur. Okay. Okay. So one really interesting fact too, and kind of goes back to the previous point about your body kind of forming microcirculation vessels on its own, is that by itself, oxygen can diffuse anywhere between a length of 20 to 200 microns. Okay? So that's how far the oxygen can kind of travel on its own. Okay? What's fascinating is that your body actually knows this. And so the capillaries in your body are designed in such a way that every single piece of tissue in your body, every single kind of cell, muscle, whatever in your body, is never too far away from a capillary. And so most muscles in your body are within about 100 microns of a capillary, within your body, right? And of course, some tissues are located closer. And as let's say that you're active and you have a very well-developed microcirculation, then this number can be reduced to something like 50 microns. Okay. And so if you're in a situation where your body is kind of demanding more nutrients, more oxygen, then part of the reason why it does that is to kind of minimize this transport. So all of your organs, all of your muscles, all of your tissues can get oxygen in a much more speedy manner. Okay. Right. So there's a lot of actually similarities between how your cardiovascular system is designed and how cities are designed as well, right? So let's say that you're planning a city. You don't want to design the streets in a way where, or you don't want to design your neighborhoods in a way where people are kind of far away from the places that they need, right? So people aren't too far away from a grocery store. People aren't too far away from a Target or a Costco or things like that, right? And so you never want to have a situation where you have just miles and miles of just packed neighborhoods. Because then it takes a while. Because then it would take a while for people to kind of travel out to do their shopping or to go to their workplace and things like that. So actually, biologists and city planners actually have quite a lot in common, and they actually share a lot of common ground, which is, I always thought was kind of interesting. Okay, so here's a little bit more about how kind of the nutrient transport works inside the microcirculation. And so, part of what determines the amount of substance that can flow through a capillary is differences in the pressure. Okay. Some contributions to the pressure is the net hydrostatic pressure. And so this is basically just the transmural pressure difference between the fluid that's inside the microcirculation and the kind of the organs that are outside. Okay. Outside of that, there's also something called osmotic pressure, which is people kind of confuse this with hydrostatic pressure, but osmotic pressure specifically has to do with differences in water concentration. Okay. And so it's almost always you're in a situation where blood has less water per volume than the surrounding tissue. Okay. And so what that basically does is that when you're kind of in this situation, because there's less water here, and your muscles and your organs and your tissues generally have a higher water concentration. Okay. There's more water. Right. In this kind of situation, you have kind of a diffusion process taking place, right? So remember, just diffusion is always just the transport of something from a higher concentration to a lower concentration. Okay? So naturally, what tends to happen in this case is that water tends to flow in to your capillaries from here. But because of conservation of mass, as water flows in, that kind of pushes something out as well. Okay? And usually the things that get pushed out are things like O2, things like nutrients. Okay. Enzymes kind of get transported this way, hormones kind of get transported this way, vitamins, nutrients, things like that. Okay. So another kind of important contributor to the molecular transport is actually the osmotic pressure. Okay. All right, so let's talk a little bit about flow control, right? So remember we said that one of the other main functions of the microcirculation is to control the amount of flow inside your body. Okay. And so this is primarily done through the microcirculation's ability to kind of to change its diameter. Okay. And because most of the resistance, vascular resistance in your body is in the capillaries, just this ability to change its diameter actually dramatically changes the amount of resistance that can that the blood experiences going through there as well. Okay. And so if you're in certain situations, so let's say that you're exercising and you need to kind of your body's demanding more blood flow, then your microcirculation can actually dilate to kind of help encourage your blood to kind of flow more quickly, right? And this is coupled together with an increased heart rate and all of that. Okay, and so here's some kind of specific mechanisms. So there's metabolic control, and so this is driven by just oxygen demand. So whenever you're exercising or whenever you're in a stressful situation, you know, your muscles and your organs are going to demand more oxygen. Okay. And so this creates, you know, this causes your muscles to kind of release certain chemical that causes your arterioles to dilate to allow more flow. Okay. So this is probably the most common form of flow control, is that, you know, whenever your body needs it, your vessels can grow to accommodate that. Okay. There's also shear stress control. So shear stress control is control of diameter through mechanotransduction. And so by sensing the shear stress and changing its diameter, it can definitely do that. Okay. And there's also myogenic control as well. And so we talked about that earlier today. So as the microcirculation senses changes in pressure from the arterial side, it can change its diameter to kind of adapt to that. Okay. So all of these kind of factors here kind of affect the kind of the instantaneous diameter of your vessels in the microcirculation. All right, any questions on this? Okay, right, so that's all I have. So that's just kind of a really quick primer on the microcirculation. So, you know, of course, there's a lot more that has to be said, but, you know, I think that's about all, you know, we had time for today. So, for the rest of the class, if you have your projects here and you want me to take a look at it, you're running into an issue, you know, we have time for that. Have your exams up here too, so you guys can come up and pick up your exams. You know, the rest of the class is just kind of open office hours at this point. So, I mentioned at the beginning of class today is that if you're on a Windows system, there's kind of an issue right now with creating your simulation files. I'm working on that right now with the dev team to get that fixed. And so right now, you know, I think probably the #1 priority for everyone for their final project is just to get a mesh, right? And so if you're able to get a mesh, if you're able to get a few different meshes, so if you're able to get a fine mesh, which is around maybe 1 to 2 million elements, and maybe a coarse mesh that you can use for testing. Coarse mesh is anywhere between 100 to 200,000 elements. That would be perfect. So let's go ahead and you know, if you're here with your project, you can work on your mesh. You can call me over and ask questions. If you don't have your project today, you know, you guys are free to go. And then we can work on it on Thursday. But make sure you pick up your exams. If you have questions on the grading, just let me know. But yeah, I'll be making my rounds, and if you have questions on Zoom, just drop something in the chat. I'll come join you at that point too.
Sebastian. Evelyn. Oh, no.
No, like, I'm straight up, you think I'm on one of everything. That sounds like, it's like, all my work was just like, just this, like, I did it like over the file, but I'm just pretty much. All the artists just super. I didn't hear it. Did you get that? Oh, so you did just put it on. Oh. What is this? Oh, it's Singapore. I got You're supposed to take it off the activity. Let's LPQs. And then what is the reason to if I get a great everybody? You always do that the other side. We don't know.
I didn't know why I was not on for a long time.
Well, chamber with the people chamber. Yeah, you're. Because I just remember like going over and I'm like, let me just get to stuff. I was like, it's crazy the way like we use figure shit out, but it kind of like, it's like, it's because it's like made in that movie. That's why I'm like, I'm not so crazy like that. Imagine being able to figure shit out. I remember what I did wrong. I kind of it's nice with this.
I might not feel
He gave me that certain always. You can answer for this one. No, I'm not saying my problem right now. This like, this is all I had to do is I had gone to 10. Wait, are you sure this is so fucking dumb.
You pretty known as DJ. So for the branches that come from the side,
Mhm.
how would you recommend, because I know that was one of the things that you looked on my comments. How would you recommend connecting those ones? Because I took your advice for the first part
Yeah.
and those legs, it came out for the all the bottom branches and the side one. Even if I went into the thing a little bit more, it just kind of got wonky when I was moving the
Yeah, so generally speaking, if you have a vessel that's coming off to the side like this, right? So let's say this is your main vessel right here. You can see that there's a vessel that comes off right here.
Yeah.
So I think the easiest place to start the path would be probably somewhere around here. right?
Okay, now.
Because generally speaking, you know, the main vessel kind of goes like this.
Yeah.
And then this is kind of the only part where you take a cross section and actually to the vessel. Now it's tempting to start here, and it kind of looked like from your model, like, kind of looked like you started out here. But then I would still kind of try to trace this back. You have to kind of move the cursor manually.
Yeah.
So that you kind of start over here. So you want to make sure that you're going to touch here and then come to this part right here.
So I actually started at the end on the outside.
Oh, okay. I see.
Yeah.
And so in those cases, you can just kind of continue. So once you kind of reach a point where you can't see, so let's say that you're kind of inside this stuff right here.
Yeah.
Just kind of, you know, try to kind of turn on your load now. And then try to look for the location that's kind of closest to that.
So turn off the pads and then, or the model.
Yeah. Exactly. And then kind of keep going and then try to place one last point right in the middle of here.
Okay.
That way you kind of start to kind of make sure it's like.
So when doing the segmentation, I can connect it to the main.
Exactly.
Yeah.
One thing that can help too, because have you been?
Oh, no, yeah, but it's, I think it's the same thing.
For the segmentation.
Yeah, all right.
Is that the one where I just kind of do the circle?
Yeah. You may have to draw the segmentation manually. So, you know, if you're kind of inside, so let's say you cross section.
Yeah.
You know, you're not gonna use that one, because you may just have to kind of draw that's manually.
And just like say, hey, connect here.
Exactly. So if it's inside the main vessel here, it won't be shown, but it does need to kind of go in.
Yeah, because I was trying to take your advice and apply it to like where the legs were.
Yeah, but.
And then it just kept getting sideways, like the bottom kept going sideways into the other thresholds.
Yeah.
And then it said that they couldn't compute
Oh,
that.
that's what I did wrong.
Right, yeah, so once you kind of get here, the threshold kind of gets hard to use, you may have to like use a circle.
Yeah,
Circles.
Okay. All right, thank you.
Yeah.
I appreciate it.
Whatever.
Project is.
I'm just gonna write this answer and see it.
Picture.
Hey, guys.
Still have yours completely go away? I still have an R cube, so I messed up some point. Mine ended up. Well, probably like. Yeah. I'm saying, when you break. see it better.
Yes, well, it's like. I don't know, oh, I forgot how. I'm playing my friend Bobby on that Counter-Strike switch back.
Yep.
Are you gonna go over peer review on Thursday or next week?
Probably next week. I think
Okay.
once, yeah, once I gotta figure out the simulation thing first.
Yeah,
And then I
you
think,
can't do that unless.
exactly, yeah, so I think we'll probably do it, yeah, next week.
Okay, so.
Wow.
Um, Forgot.
Because like when we do the touch dot phone,
It's DHC.
It does. When you click on that phone, right, it like has nothing.
Well, that would be.
like that kind of,
I think it just like takes like an empty file and like reads everything that's.
it just reads a data file. It's a,
It sometimes reads like every other file. I don't know.
See you guys.
I mean, I did average, which the 41 was the average, but I mean, I'm still not happy about that, I guess, but, so like for, I think I just had a couple questions. What was the third element?
So the Windcastle model is a pump, a compliance chamber and a resistance. And so the pump is the one that you were missing. So
Oh, so it was resistor, capacitor, and then pump.
yes, yes.
Oh, got it.
So the Windcastle model looked like this, right? So we had kind of there's kind of like a pump that looks like this. I just do the box. And then there is a kind of a balloon.
Yeah.
So the balloon kind of represents kind of the flow store. So this right here is your compliance or capacitor. And then at the end here, you have kind of these micro channels here. So this right here is your resistance. So you got the resistance and the capacitance, and I think you did a pretty good job kind of explaining their purpose.
Thank you.
But the main thing I was looking at, the Windcastle model was mostly to emulate the waveforms, right? So the pressure waveform kind of looks like this. Right, so we have kind of this kind of this part where the pressure kind of increases, that comes directly from the pump. So the pump is basically like the heart. So when the heart contracts, it kind of pumps, goes up like this, and you have kind of a slow decrease in the pressure. That's because of the capacitor right here is kind of slowly letting flow out. Okay. And then for the flow waveform kind of looks something like this. So they have a big amount of flow and then kind of a small amount of flow like that. And so it's kind of talking about kind of these three components and how they contribute to these things right here. So yeah, the main thing that you're missing is like the heart.
And this was all on 476A. I literally know this stuff too.
Oh, I see.
And then for this one, I lost like 2 points, I think. Was it just because, I mean, I guess, yeah, those were kind of extra stuff then, huh?
It was extra stuff. Yeah. So I mean, what you wrote down here was good.
Uh-huh.
But yeah, all the stuff up here was kind of not necessary, because I was just kind of worried just about.
Yeah, did you want like more information on?
No, this was good too, but then I noticed this a lot. So I've been kind of cracking down on more lately. People kind of just put down just as much information as they can of things that might be related. So so I kind of just take some points off of that.
For adding an extra stuff.
Yeah,
Okay.
yeah.
I thought that it would have done like the opposite. Should I understand more?
No, yeah, it's kind of like a spray. It seems like a spray and pray type of approach. So
I mean, I still have like the correct stuff though.
yeah, that's why I gave you the 4 points for it.
Yeah, this one I had no idea. This one I did good. And then this one, was it just were you looking for just Q of L instead of
Exactly. Yeah. So
I have it right here too. That's
so this last element here is an inductor.
uh-huh.
So the flow on the inductor is something that you compute directly from this equation here.
Yeah.
And so if you have pressure over inductance, that's usually doesn't really make that much sense. And so this would just be the QL.
Okay.
But I can tell your logic was sound. That's why I just marked up one.
Yeah. It's just a dumb mistake because I literally have it right there. This one I need to just I think I need to just review it on my own in general. I don't think I understood this one.
Yeah, so this was a problem on the last homework that we did, basically. So you have this flow waveform here. So this one basically, you just take this and you just plug in here, basically.
Okay.
So we did this during the 1D equations, where this in the lecture, this was just a quadratic function.
Okay.
And so we plug it in there, and then we ended up with a factor of like 4/3, right? And so when you plug this one in here, this is a cubic function, and so you're going to get a different factor here. So I want you to look for kind of this number here.
Okay.
So the homework problem, I gave you a harder function on the homework, which is the
Mhm.
cosine function. So that one was much more difficult to integrate. This one was just a
Yeah, I
cubic
kind
function.
of just followed the homework, which, yeah, I don't really I guess I just need to review this one on my own completely.
Right.
I think that was it then. Okay. Thank you.
Yep. Mhm.
I guess I just need to work more on the final then, so if I'm